Okay, a couple announcements before we get started. Your exam 2B, which is on NMR, will open today at 12:15. You'll have 24 hours to do that. Please review and your work before you submit. Make sure you go ahead and submit that. Interim grades are due Friday, so after Wednesday, what I'll do is make sure that the zip grade and Canvas rosters are correct. Then I'll move your scores from zip grade into Canvas so you'll see them there. And you will see your Z-score and rank in the course to know where you stand. Your Z-score is basically a measure of your performance relative to everyone else in the class. If it's positive, you're doing well. If it's negative, you probably want to do a little revision of how you approach the class. And your rank is where you stand amongst the other 163 students in the class. Any questions on grades or scores? So again, you can download the Excel file. It'll tell you kind of where your grade trajectory is with the current number of points in the class. So with that, I thought what we would do today is put it all together, look at a couple different, 4 different problems where we'll see what the data is telling us, try to put together a structural claim and see if everything fits. So this first problem here has the IR mass spec, carbon and proton all in one. I've covered up the molecular formula, so one thing we'll do as we walk through this is figure out what that is, do the degrees of unsaturation, see what functional group that belongs to, and make sure that the carbon and proton NMR align with what we're claiming. So this first one I'll kind of walk you through. The other ones I'll give you some time to consider before we start discussing things. So since we're given all of the data at once, let's just go ahead and look at the IR first, see what we can figure out based on the signatures in the different regions. That will lead us to some functional group claims. And then as you'll see, we can start accounting for some carbons, some heteroatoms, and that's how we're going to figure out the molecular formula. So the first thing, when I look at this, I see this kind of broad hump here right in region 1. I always sort of draw a cutoff there, but that belongs to an OH. And the way that it looks, we can see that there's this signal here at 1715. That's going to belong to a carbonyl group. So those two together are a carboxylic acid. So if we jam them together, we've come up with that fragment. So far we have 1 carbon, 2 oxygens, a hydrogen, and 1 degree of unsaturation. Now, if we move to the mass spec data, we can see that the parent ion is 74. So 74 is even. So that tells us there's not an odd number of nitrogens present. The other sort of clues to look for, it's kind of hard to see. The M+1 and M+2 regions, there's really nothing there that is diagnostic for a halogen, so specifically chlorine or bromine. We would see a significant M+2 and it would be listed there. So there's no chlorines, there's no bromines. One other sort of logical thing, since the parent of 74 must contain all of the elements of the molecular formula, the atomic mass of bromine is 79. So 74 is 5 less than that, so there can't be a bromine. That mass could contain chlorine, but since the M+2 signature for chlorine is not listed, we can eliminate that as well. So really what we're doing moving forward is just considering that of the 74, the only heteroatoms are those 2 oxygens. So we could take 74 minus 2 times 16, that's the oxygen contribution, and then everything remaining is C and H. So I'm not going to write that down. I'm going to sort of present it another way. And we're going to move over to the carbon NMR now. So I get these problems from a workbook where each kind of page has this data. And in this workbook, they have the carbon. That's what you're normally used to seeing here. It says proton decoupled. That's just what we've been talking about, where each carbon signal is a line. This thing here is the solvent that the sample is dissolved in, and we do not consider that when we count. So if we just count the lines, how many are there? So there's 3. So we can make sort of a first approximation that of the 74, 36 of the mass units belong to carbon. It could be more if there was symmetry. We don't know that yet. When we look at the 3, we have 1, 2, 3. Now, we already know that there is a carbon due to the carboxylic acid, and that's sp2 hybridized. So of the 1, 2, 3, we can assign that signal to the sp2 hybridized carbon. So that leaves us 2 signals. And what does their hybridization have to be based on the region they're located? So both of these have to be sp3 hybridized. So from 0 to about 80, that was your sp3. So 80 to about 110, that was sp. And then 110 up to 220 was sp2. Now, what is new today, see this thing above it, this stacked carbon spectrum? It says DEPT. You don't have to know this, but it stands for distortionless enhancement by polarization transfer. The fancy word for that is, again, there's the NMR is detecting the nuclear spin. So the spin can be up or down, but between those 180 degrees of being up or down, the radio wave can pulse at a certain angle. And from that information, what you see on this stack plot is the attached hydrogens. So DEPT is also called APT, or attached proton test. You see the key here? It says CH2 down, CH3, CH up. That deals with the phasing relative to the baseline. So if you see a signal that's up, it has to be CH3 or CH. If it's down, it has to be CH2. So of the two remaining signals, we know they're sp3 hybridized. How many hydrogens are attached? This one right here has to be a CH2 group. So that's a second fragment. Our first fragment was an acid. Our second fragment was a methylene CH2 group. And then the third one, because it's positively phased, it could be CH or CH3. You could probably make a guess as to what it is. But let's go down now to the proton to validate with 100% confidence what exactly it is. So this is our normal proton spectrum, 0 to the right, 10 to the left. When we count the unique sets, see this offset here at 11? It says exchanges with D2O. So that's one set. Then we have this thing here about 2.5, that's a second set. And then at 1, that's the third set. So we have 3 unique sets. Now we need to figure out what the ratio is, and that's going to give us the total hydrogen count. So this thing right here at 11 says exchanges with D2O. We already know from the IR there's an OH group. So hydrogens that are attached to heteroatoms will exchange with D2O. So what does that mean? So that H becomes deuterium, and that's an acid-base reaction, which leads us into the next module that will start on Wednesday. But that's an assignment. So we've assigned one of the H's to the acid. And we have these 2 other sets. See these numbers in blue? So those are the ratios. So obviously you can't have, a carbon with 12 hydrogens attached to it. So we're going to do this thing that we learned in Gen Chem when we were figuring out empirical formulas. We're going to take those numbers, divide it by some other number to get the actual attached hydrogens. So of 8 and 12, what do you think we should divide by? What number? So we'll divide by 4. So that gives us 3 and 2. So what that's saying is this signal at 2.5 has 2 attached hydrogens. And we know that from the carbon NMR because of that depth spectrum. So that has to be a CH2. So therefore, the remaining one that we were unsure of now has to be a CH3 group. So our third fragment is CH3. So from all of this data, we have an acid fragment, a methylene fragment, and a methyl fragment. So now we're going to use the rules for Lewis dot, combine those things to come up with a structure. So we should probably start from this, the CH2, because that has two open things to attach fragments to. If you try to bond the methyl group to that, you're not considering that, and so that would not lead to a valid claim. So if we just stick that on there and that on there, we can arrive at a structure. And so it would be off the screen. Let me draw it on the screen. That 3-carbon carboxylic acid. So a couple things to point out. The carbon NMR is actually showing all of the carbons. There's no symmetry that's going to reduce the carbon count. So we have 1, 2, 3. So of that, 36 of the 74 mass units will belong to carbon. And then we end up with 6 hydrogens. So we can see that from these ratios, 3 plus 2 plus 1. The degree of unsaturation we're assigning to the carbonyl. So if we were to present this in front of the judge, I think it'd be bulletproof. There would be no way to argue anything other than what we're proposing. Any questions? Yeah.
Why did we have to use the proton NMR to figure out that the third one was CH3? Like, why couldn't we have just seen that the carbon spectrum, like it was turned upwards?
I wanted to just lead everyone through just to make sure that we were all on the same page with that. If you get it, then you would say, yes, that has to be a CH3 group. But, you know, there is a little asterisk to that statement because in the stack plot, things that are positively phased could also be CH. So if we're following the logic, we know that that has to be CH3 because if we claim it's CH, that's going to have a fragment with 3 open things to it, but we don't have enough other stuff to put on there. But you might run into a situation where you have a positively phased carbon and it's not as clear as it's CH3 versus CH. So you really have to hop back and forth between carbon and proton to make sure that the integrations in the proton are lining up for CH or CH3. Any other questions? So here's another set of data from that same book. I've retracted the names of the people involved here, so the molecular formula is not shown, not releasing the data. You got to figure out from what is there, how many carbons, how many hydrogens, and then what are the heteroatoms. So I'll give you about 5 minutes to see what sort of fragments you can come up with. Then of those fragments, how are you going to bond them together? And then we'll circle back and start putting some things together.
I have a question. For the mass spec, is the M172? Thank you.
Any volunteers come up to the board and write a structure?
Is that? It would be VR.
Anyone else? So what do you think? Any Kenny Wayne Shepherd fans in the crowd? We got blue on black up there. You like blue or black? Which one? So the two structures as drawn are isomers, but one of them it fits the data a little bit better. So show of hands, who likes this one? We have one or two very hesitant. Who likes that one? Who doesn't care? I appreciate the honesty. Well, let me show you one more thing. So those would be three possible isomers that would fit that data. The difference is, so they all have the benzene ring. The difference is the relationship between the bromine and the alcohol. So the IR, I'll write this down. The IR shows you the presence of the OH. The mass spec tells you the presence of the bromine. Then as you analyze the carbon in the proton, it's going to sort of eliminate some based on either, and then it's going to zero into the best plane. So the one in blue is the correct one. So how do we arrive at that? Let's pick through these things. And then as we do it, we'll eliminate the other claims. So one thing I do want to point out, textbooks are a very sterile version of facts and history. So when you see data in a textbook, it looks nice and clean. When you actually see data in real life, it's not the best looking thing. But so that right there is an OH. Even though it doesn't look like the perfect OH group, at least we know it's a fragment of an alcohol. When we go down to 16 to 1800 here, there's no carbonyl. There's this thing here, but it's at 1600. That's too far low to be a CO double bond stretch. So the only thing we're really getting from the IR is there's an OH group. But at least we know one of the heteroatoms now is oxygen.
Is there a C double bond C group on the IR?
Yeah, so that's probably the sort of double bond thing right there.
Is
What-
that how you can kind of tell that it's aromatic too? It's like could that help us?
It can, but again, once you get sort of around 1600, the ambiguity starts to creep in. The aromatic part is better seen like in the carbon, in the proton data, and I'll point it out there. So we have that heteroatom. We move to the mass spec. We can see that there's the parent at 172, and then it has another signal at 174. So M and M plus 2, it's kind of hard to see, but the ratio is 1 to 1. So that's telling us there's a bromine. So that's another heteroatom, another fragment. So right now we have two fragments to work with. We could take that 174, subtract out 79 and 16. That would get us the remaining CH count. But another way of doing it is just going to the carbon and proton and figuring it out that way. So how many signals are there in the carbon NMR? So there's 6 unique signals. We don't count that solvent. When you look at the depth, this is the stacked one above it. So we count 1, 2, 3, 4, 5, 6. When you look above it, you see 2 of those do not have any corresponding signal. That means those carbons have no attached hydrogens. So 4 of those 6, because they're positively phased and the region they're in, these must be CH groups. These cannot be CH3 groups, because this region of the carbon is for sp2 hybridized carbon atoms. So if it's sp2, the maximum number of attached hydrogens is 2. You can't have a CH3. So to answer the question about aromatic, when you start seeing these patterns, because all of those 6 signals are in this region, we're going to assume that that belongs to a benzene ring. So benzene's nice because it's 6 carbon atoms. They're all sp2 hybridized. So we can draw that fragment now. So that's 6. Then we have these 2 other fragments, and really what we're figuring out now is how are they bonded? Are they next to each other? Are they sort of 3 away? And it is showing on the screen, or are they 4 away? So without even going to the proton just yet, if you look at these 3 possibilities, how many unique carbons should this one have? This one should have 6. How many unique carbons should this one have? 6 as well. And then this one, 4. It can't be that one, because the carbon data is showing 6 unique signals. So we've eliminated that as an isomer. So now what we have to do is go to the proton data and say, how are the substituents arranged, either in this 1, 2, or 1, 3 fashion? The H of the OH is common to both, but then when we look at these, we'll have 1, 2, 3, 4 signals. 1, 2, 3, 4. So the proton NMR data, this thing right here in the middle, that's the H of the alcohol. The expansion that's shown right here shows 1, 2, 3, 4 signals. So that doesn't solve the problem just yet. So what do we do next? We have to look at the splitting pattern. And that's what is going to differentiate the one in blue from the one in black. Before we get to that, it says each integral is 9 millimeters. All I did was take a ruler and measure this line right here, that integral curve. If you take 9, divide it by 9, you get 1, so that's our ratio. 1H, 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 1H. So total we have 5 signals, and they're all 1 proton. And that, again, is confirmed up by this attached proton test in the depth. Before we analyze this splitting here, let's just do it on the board real quick in terms of the number of neighbors. So all of these 4 hydrogens are unique because the molecule, the symmetry exists in the plane of the board, and that really doesn't count. It has to be sort of orthogonal. So the way that we can get to the blue one is the correct one. If this is a unique proton, how many neighbors does it have? It has 1, so it should appear as what? A doublet. And then this one should be, that one should be a triplet. So we'll do this, and then I'll explain sort of an issue with the triplet assignment. So we have 2 doublets, 2 triplets. What should this one be? Singlet. So a singlet. This one should be the doublet, triplet, and doublet. So the thing we can use to eliminate now is that. When we look at those 4 signals, none of them is a singlet. So that's how we arrive at placing the OH and the bromine next to each other on the ring. So we said for the blue one, 2 doublets, 2 triplets. So we have a doublet, a triplet, and a triplet. See this, what do we want to do? I guess for all of them, it's kind of relevant. See at the top there, there's that little splitting at the top. So far, to our first approximation, we've been saying the splitting is just due to the neighbor. So like if you look at the doublets, they have that little blip at the top, which is another smaller splitting, which is a doublet. So in aromatic systems, what happens, because this molecule does not have symmetry, this H is coupled to that gives you the big split. But then that little thing at the top can actually be split by this too, for reasons we kind of asked the question, what ultimately gives rise to splitting? And really it's the transmission of that spin information through orbitals. So this hydrogen feels that spin because of, so that's a bond, right? So when we make bonds, there's always, we make a bond and then what else do we make? Because we have 2 atoms, carbon and H. They come together, they're supplying, each supplies 1 orbital that's 2. They make a bonding orbital and then an anti-bonding orbital. So the way those orbitals sit, the spin information from this is transferred to that. That's why you get that little B splitting at the top. So for these two, even though we're calling it a triplet, for the most part, it would probably be called a doublet of doublets. Because that H and that H are not equivalent. And then just by looking at sort of the gross or big structure of the signals, none of them is a single. So that's how we eliminate that. So when you're going through this data, there's these different levels at which you can start rejecting claims. But if you end up in this situation where there's 6 carbons, there's 4 unique set or 5 unique sets of H for both, then you have to go down another level of analysis. So the best claim for this one was the 2-bromophenol. So the other thing, again, I don't want you to think I'm ducking the answer about aromaticity and the IR. It's really hard to determine if there's a benzene ring in the IR, just because the signals are not very strong. So the better way to do it is looking at the chemical shifts in the carbon, and then this region in the proton. Again, there is some overlap here with alkenes, but if you have a lot of carbons here, that's going to be a good indicator that you do have an aromatic ring. Questions on that one? So the first two were from a book that I have. This next one is from, I don't know, even know where that is, Switzerland or something. This is some European website that has these problem sets. This one, you're only given the proton and the carbon data. See how this says apt? That's attached proton test. You do have the molecular formula now, but you don't have IR or mass spec. Let me say for this carbon, I think the apt is phased differently on this one. So your CH and CH3s are down and your CH2s are up. So see what you can figure out in the next 5 or so minutes for any structural claims, and then we'll review. I have one addendum to the item here. See this little blip here? So because this is apt, it is showing you all of the carbons. So that little blip has no hydrogens attached. See how it's up? If we consider 0 even, so C and CH2s are up. So a depth would not show a signal there. So this little blip right there is a signal.
What about the one closer down?
Right here,
Yeah, that one's not.
that's the solvent.
Okay.
So you don't have to consider that. So did anyone use the molecular formula to figure out degrees of unsaturation? What? How many unique sets of hydrogens are there? And then what's the ratio? So you get that information from these little numbers here. I just like to write them in descending order. So when we find that ratio, we sum it up together, we get 10. That matches the molecular formula, so that accounts for that. How many unique carbons are there? So there's 9 total carbons, but how many signals do we see? So because we only see 7, that means there's some form of symmetry in the molecule. What could you tell me about the cluster of signals in the proton between 7.3, 7.4, and then these signals in the carbon? What sort of functional group do they belong to? What? Close, but not quite. So what hybridization are these carbons? Those have to be sp2. So based on the location of those signals and the location of these, plus that number, what do you think those carbons and hydrogens belong to? It has to belong to a benzene ring. So benzene is C6H6. That number is 5. So that's telling you one of those hydrogens has been substituted for whatever else is remaining. There's a ring plus 3 pi bonds, that's 4 degrees of unsaturation. We said there were 5 total, we have 1 left. What do you think the 1 degree of unsaturation belongs to? What functional group? What type of carbonyl? So see this peak at 200? That has to be the carbonyl carbon. Notice how it's phased down? If it's phased down, it has to be CH or CH3. If it is sp2 hybridized, it has to be CH. So therefore, what functional group is that? An aldehyde. So we have 2 fragments. We have a benzene ring, we have an aldehyde. We can't attach them together yet because we have not considered the signals here in the carbon and then these signals in the proton. So far we've accounted for the 1H, so that H belongs to the aldehyde, these 5 belong to the ring. Then we have 2 and 2, that's what we see here. What can you tell me about the multiplicity of those signals? What are they? They're both singlets, which means what? They have no neighbors. So because of the integrations are 2, we know they're CH2 groups. That's confirmed by this phasing in the APT spectrum. So now we have benzene ring, methylene, methylene, and aldehyde. So how do we connect those things? Number 1, so that you end up with signals in that region. And number 2, they have no neighbors. Who wants to come ring the bell, draw a structure? What? We've accounted for 1 oxygen. So you got to stick the other one in there somewhere so that it obeys all that proton and carbon data. So really what it boils down to one, two, three, four. That 5th fragment, that 2nd oxygen, you got to stick all those together to meet the criteria of the chemical shifts in the carbon and the proton, and more importantly, the lack of neighbors. So stated another way, you have to isolate those CH2 groups so there's no neighboring H groups. You want to come down and ring the bell, as it were? Yeah, that's right. Anyone else get that? That's what I got, so two beats silence. So if you look at the claim here, I think it sort of meets any, we can reject other things where the CH2 groups are bonded together, because then that's going to lead to splitting. When I looked at this problem at 10:15 this morning, to me, the tricky thing is the chemical shifts of the proton and carbon. So that 4 and 4.5, along with the stuff at 75, it's crucial that those CH2 groups both be bonded to an oxygen to move them into that region. And then the other thing is you have to isolate them so they appear as singlets. If you try to arrange this stuff any other way, you're not going to meet that data exactly. Yeah?
Why would the hydrogen on the aldehyde not be considered a neighbor to that CH2?
So let me draw the structure first, and then I'll get to that. So the question was, we have this aldehyde H. That's the thing at like 9.58 or something. So it appears as a singlet, but it has these two neighbors. So why isn't it splitting that into a triplet, or why isn't that splitting into a doublet? The cheapest explanation I can give for that, so that carbon is sp2, that's sp3. Sometimes you see that, sometimes you don't. I don't know the theoretical reason of why it isn't consistent. I would say more often it occurs as just a singlet. So this website here is nice. They have 3 categories: easy, medium, and difficult. There's probably about 100 problems total that you can look through. Again, if you try to take those different fragments and rearrange them in a different way, you're going to violate some of the data that you see. Any questions on that one? So the last problem is from Notre Dame. They have another set of spectroscopy problems where you're given mass spec, IR, carbon, and proton data. That's what the rest of these slides are. They belong to one problem. And what I thought we would do is just go through each one and then see by the time we get to the last one if we can figure out what the structure is. So here's the mass spec data. And so are there anything you can confirm or reject based on what you see? So I heard no nitrogens. I think I heard no iodine. There's no 127 peak. So no chlorine or bromine. So now this is, again, what you have to pay attention to. probably hard to see, but that's an M+1 signal. It's not M+2. So M+1 really only tells you the carbon count. The M+2 will tell you if it's bromine or chlorine. And because we're kind of solving this another way, if we did just this cheap algorithm where we took 166 and divide by 12, what would the maximum number of carbons be? So my calculator said 13.8. Let me just backtrack that. 14 times 12. That get 14 times 12 is 168. That's beyond the parent. So if it was 13 as the maximum number of carbons, that would be 156, and then we would end up with 10 hydrogens. So our upper bound is 13, but as we'll see when we go through the other data, we're going to start reducing that number to a more accurate molecular formula. That's just one way I do it for carbon specifically. Another way you could do it is if you took C and H, that would be 13, and that you can arrive at a similar approximation for CH equivalents. So what about the IR? What can we learn about that? Anything else in there that stands out? So the way that those two things look together, we're going to lump them and call it a carboxylic acid. So that tells us there's at least 1 degree of unsaturation. There's at least 2 oxygens. So of the 13, we kind of know 1 is at least going to be sp2 hybridized. I think that's all we can get out of that for now. So here's the carbon NMR. How many unique carbons are there? How many of those carbons are sp3 hybridized? How many are sp2? So remember, in this region, 1, 2, 3, 4, 5, all of those are sp2. So we can sort of now start refining a little bit. 7 carbons times 12, that gets us 84. But again, if there's symmetry, there could be a greater carbon count than 7. So we're between 7 and 13 now. We're trying to narrow it down. So we're going to run out of time, but when you look at these, see this split right here from 158 to 177? We already said that there's a carboxylic acid, right? So that carbon has to belong to a carboxylic acid. That leaves us with 1, 2, 3, 4 amongst that spread. What that's telling us that these are aromatic carbons of a benzene ring. And so now we have to figure out the symmetry of the ring and what else is attached to it. Here's the proton, just 10 more seconds. What you can do is count the unique sets. The ratios are given to you. And then here's the blow up of those sets. So now you have to look at the multiplicities to make sure that you're connecting the fragments right. So see if you can figure out the structure from that. The structure ends up being this carboxylic acid. And the thing to note is there's a presence of a third oxygen. And you can arrive at that doing the math of the carbon count, the hydrogen count, and the fact that this triplet around 4 ppm has to be bonded to an electronegative atom, so that triplet is there, and that's going to help explain how it moves there. And then the mass that you're left over with gives you 3 oxygen atoms.